Welcome to another webinar session by Academics, a technical training division of EGS Computers India Private Limited. Today, we have an interesting topic called Stress-Based Fatigue Life Evaluation of Mechanical Structures. We shall be covering both analytical and FEA methods for this topic. This webinar is divided into two sessions, Session 1 and Session 2. In the first session, we shall go through the details of fatigue life methods, endurance limit modifying factors, fatigue strength, stress concentration factor, notch sensitivity, etc. Some basic problems related to fatigue life evaluation shall be discussed with analytical solutions. In the second session, we shall go through the numerical solution of same problems with finite element analysis method and the comparison of analytical and FEA methods. In most of the material testing procedures, the load is applying in a gradual manner because in order to get the material properties related to stress strain diagram, it is necessary to give enough time for the strain to fully develop. Here, the specimen is undergoing a destructive test. That means the stresses are only applied once. The condition for this type of testing is called static condition. Such conditions closely approximate the actual conditions to which many structural and machine members are subjected. However, there are several situations frequently occurs in which the stresses changes over time or fluctuate between distinct levels. For example, consider a small fiber on the surface of a rotating shaft which is subjected to bending loads. This shaft may undergo a tensile load or a compressive load or a combination of both. Let's say the shaft undergoes both tension and compression for each revolution of shaft. If the shaft is rotating at 1800 rpm, the fiber may stress in the tension and the compression 1800 times in each minute. The stress induced on the fiber is called alternating or fluctuating stress, and the condition is called dynamic condition. Due to these stresses, shaft may fail at some point. Most of the analysis reveals that the actual maximum stresses were well below the ultimate strength of the material and quite frequently even below the yield strength. The most distinguishing characteristic of these failures is that stresses have been repeated a very large number of times. Hence, the failure is called a fatigue failure. Let's look at the section view of the failure area. The fatigue fracture failure arising from three stages of development. Stage 1 is the initiation of one or more microcracks due to cyclic plastic deformation followed by crystallographic propagation, which extends from 2 to 5 grains above the origin. Stage 1 cracks are not normally visible to the naked eye. Stage 2 progresses from microcracks to macrocracks, forming parallel plateau-like fracture surfaces separated by longitudinal ridges. The plateaus are generally smooth and normal to the direction of maximum tensile stress. Stage 3 occurs during the final stress cycle when the remaining material cannot support the loads, resulting in a sudden fast fracture. Stage 3 fracture called chevron lines, which point towards the origins of the initial cracks. What are the reasons for fatigue failure? Fatigue failure is due to crack formation and propagation. A fatigue crack will typically initiate at a discontinuity in the material, where cyclic stress is at maximum. Discontinuities can arise because of design of rapid changes where stress concentration occurs, components that roll or slide against one another under intense contact pressure, locations of stamp marks, tool marks, scratches, composition of material, surface and subsurface discontinuities, inclusion of foreign materials, etc. Various conditions like residual tensile stresses, elevated temperatures, cycling temperature. Three major approaches used in design and analysis to predict when, if ever, a cyclically loaded machine component will fail in fatigue over a period are presented. The first one is stress life method, strain life method, linear elastic fracture mechanics method. The stress life method based on stress levels only. It is the most traditional method since it is the easiest to implement for a wide range of design applications. This method has sufficient supporting data and represents high cycle applications effectively. The strain life method involves more detailed analysis of plastic deformation at localized regions where the stresses and strains are considered for estimating life. This method is especially good for low cycle fatigue applications. The fracture mechanics method assumes a crack is already present and detected. It is then employed to predict crack growth with respect to stress intensity. It is most practical when applied to large structures in conjunction with computer codes and a periodic inspection program. To determine the strength of materials under the action of fatigue loads, specimens are subjected to repeated or varying forces of specified magnitudes, while the cycles or stress reversals are counted to destruction. The most widely used fatigue testing device is the RR Moore high-speed rotating beam machine. This machine subjects the specimen to pure bending by means of weights. That is, there is no transverse shear. The first test is made at a stress that is somewhat under the ultimate strength of the material. The second test is made at a stress that is less than that used in the first. This process is continued. The results are plotted as an SN diagram. This chart may be plotted on semi-log paper or on log paper. Fatigue failure from 1 to 1000 cycles is generally called low cycle fatigue. Failure greater than 1000 cycles is high cycle fatigue. We can also distinguish a finite life region and an infinite life region. Due to the nature of some rotating machinery, fluctuating stresses in it frequently take the form of a sinusoidal pattern. Other patterns, some rather irregular, do exist though. It has been discovered that the shape of the wave is not significant in periodic patterns with a single maximum and minimum of force, but the peaks on the high side and the low side are. As a result, it is possible to describe the force pattern using F max and F minimum in a cycle of force. It is also true that describing the force pattern by ranging above and below a baseline can be just as useful. The construction of a steady component and an alternating component can be done as follows. If the biggest force is F max and the smallest force is F minimum. The mid-range steady component of this fluctuating force is the average of maximum and minimum force. Amplitude component is the modulus value of half of the difference between maximum and minimum force. Let's see some of the various stress time traces that occurs. The first one is fluctuating stress with high frequency ripple. Two types of non-sinusoidal stresses. The fourth one is a sinusoidal stress. Fifth one is a repeated stress. And the sixth one is a completely reversed sinusoidal stress. Let's take the sinusoidal fluctuating stress, where sigma minimum is the minimum stress, sigma max is the maximum stress, sigma A is the amplitude component, sigma M is the mid-range component, sigma R is the range of stress, sigma S is a static or steady stress. Let's check the relation between these values. The mid-range component sigma M of the sinusoidal fluctuating stress is the average of maximum and minimum stress. Amplitude component sigma A is the modulus value of half of the difference between maximum and minimum stress. The stress ratio R is the ratio between minimum stress and maximum stress. Amplitude ratio A is the ratio of amplitude component and mid-range component. For most of the applications, we just want to design a part to have infinite life. Let's see the interaction of mean and alternating stresses on the fatigue life of a material. Here, we have mean stress on x-axis and alternating stress on y-axis. Line connecting between the ultimate strength value in x-axis and endurance limit in y-axis give the Goodman relation. We assume that any combination of mean stress and alternating stress that comes under this area wouldn't cause the part to fail. Let's assume a combination of mean stress and alternating stress at B. Since this B is under the safe line, the part having with the combination stress won't fail due to fatigue. Factor of safety for this specific combination shall be the ratio of the length of line from origin to safe line, that is OA, to the length of line from origin to the stress state, that is OB. This is the equation for Goodman relation. This equation used to quantify the interaction of mean and alternative stresses on the fatigue life of a material. Like Goodman, we have Solidworks criteria that connects endurance limit and yield strength. These two are two conservative criteria. From the lab results or from experimental data, plots fit data better like Gerber, which connects endurance limit and ultimate strength, or ASME elliptic criteria, which connects endurance limit and ultimate strength. These are the relation for the four criteria: Goodman, Soderberg, Gerber, ASME. These are the respective factor of safeties for Goodman, Soderberg, Gerber, ASME elliptic. We have already mentioned the term endurance limit. For the fatigue life calculation, the value of endurance limit is essential. So, what is endurance limit? It is defined as the stress range below which there is no crack growth and material shows infinite life under the cyclic stress. For preliminary and prototype design and for some failure analysis as well, we require a quick method for estimating endurance limits. Here, we have a reference graph of endurance limits versus tensile strength from actual test results for a large number of wrought irons and steels. From this graph, for the steel structure, the estimate for the endurance limit can be represented like this, where SUT is the minimum tensile strength and S prime E is the rotary beam test specimen endurance limit. For an actual mechanical component, the relation for endurance strength with the number of cycles to failure can be represented like this, where SF is the endurance strength and N is the number of cycles to failure, and A and B are the constants. For a completely reversed stress, we can set the endurance strength to reversed stress. Therefore, we can rewrite the above equation like this. From this, we can write the number of cycles to failure. In the relation, we have seen the constants A and B. The relation for A and B are where F is the fatigue strength fraction and SE is the endurance limit at the critical location of machine part. The value of fatigue strength fraction can be obtained from the graph with ultimate strength in x-axis and fatigue strength fraction in y-axis. Let's see an example. If we have an ultimate strength value of 840 megapascal and if we are plotting the values with the y-axis, we get the value for fatigue strength fraction. We have seen that the rotating beam specimen used in the lab to establish endurance limit is thoroughly prepared and put through testing under tightly controlled circumstances. It is unrealistic to anticipate that a mechanical or structural member's endurance limit will match laboratory measurements. Therefore, differences in material, manufacturing, environment, design, etc. have to be considered. In order to incorporate this difference, Mr. Joseph Marin identified factors that quantified the effects of surface condition, size, loading, temperature and miscellaneous item. Therefore, a Marin equation is written as like this, where SC is the endurance limit at the critical location, K is the surface condition modification factor, KB is the size modification factor, Kc is the load modification factor, Kd is the temperature modification factor, Ke is the reliability factor, Kf is the miscellaneous effects modification factor, S prime is the rotary beam test specification endurance limit. Let's see each modifying factors. The first one is surface modification factor Ka. The surface modification factor depends on the quality of the finish of the actual part surface. To find quantitative expression for common finishes of machine parts like ground, machined or cold drawn, hot rolled, as forged can be expressed like this. The second one is Kb, the size factor. For bending and torsion, size factor is like this, and for axial loading, since there is no effect on axial loading, Kb is equal to 1. The third one is the load factor. It is a function of the ultimate strength. The variation is minor, so it is appropriate to specify average values of the load factor. The fourth one is the temperature factor. When operating temperatures are below room temperature, brittle fracture is a strong possibility and it should be investigated first. When the operating temperatures are higher than room temperature, yielding should be investigated first because yield strength drops off so rapidly with temperature. For this, temperature factor is represented like this. The fifth one is the reliability factor. Here we have to account for the scatter of data as we have shown in the SN diagram earlier. Thus, the reliability modification factor that has to be accounted for is written as like this. The value of transformation variate is shown in the table. The sixth one is miscellaneous effect factor. This factor is intended to account for the reduction in endurance limit due to all other effects. It is really intended as a reminder that these factors must be accounted for because actual values of miscellaneous effect factor are not always available. After calculating and putting the values of Marin factors in the equation, we get the endurance limit value. The values of constants A and B can be obtained once we input the values of endurance limit and the fatigue strength fraction in the respective relations. Finally, the values of constant A and B can be plugged into the relation of number of cycles to failure. We mentioned the existence of irregularities or the discontinuities such as holes, grooves, notches, fillets in a part. These discontinuities increase the theoretical stresses significantly in the immediate vicinity of the discontinuity. To obtain maximum resulting stress using nominal stress due to this irregularity, we are using a factor called stress concentration factor. Some materials are not fully sensitive to the presence of discontinuities. There, we can use the reduced value of stress concentration factor called fatigue stress concentration factor Kf. Its relation is Kf is equal to 1 plus Q Kt minus 1, where Q is called the notch sensitivity. Notch sensitivity Q is defined by the equation like this. The value of Q is in between 0 and 1. The value of Q can be found from the graph with notch radius in x-axis and notch sensitivity in y-axis. That is, by plotting the values using the notch radius and a suitable ultimate strength value, we can find out the value of notch sensitivity. Also, the notch sensitivity can be found out by another relation, that is, here root A is called the Newberg constant and R is the notch radius. The values for Newberg constant for bending and axle is given as. This relation is for torsion. Let's go through some examples. We have the first problem, plate with hole. The code drawn ASI 1035 steel bar shown in the figure is subjected to a completely reversed axial load fluctuating between 28 kN in compression to 28 kN in tension. Estimate the fatigue factor of safety and the number of cycles to failure. Also, we have the additional data. Material is ASI 1035. Ultimate strength is 585 megapascal. And the endurance specific limit is 205 megapascal. That is, F max is 28 kilonewton, F minimum is minus 28 kilonewton. Using the Marin's relation, we can calculate the values. Surface modification factor Ka as 0.83. Since it is an axial loading, the load factor Kc is taken as 0.85. All other remaining modifying factors are taken as 1. We know the relation for endurance limit. Substituting the values of modifying factors and the test specimen endurance limit value in the equation, we get the limit value as 143.5 MPa. From the notch sensitivity chart for the ultimate strength of 585 megapascal and for a notch radius of 3 mm, we get notch sensitivity value Q as 0.83. We know the diameter value of notch D as 6 mm and width of the plate W as 25 mm. Therefore, the D by W ratio is obtained as 0.24. From the chart of theoretical stress concentration factor for a plate in tension or simple compression with a transverse hole, for D by W of 0.24, we get the stress concentration factor as 2.44. Substituting this value in fatigue stress concentration factor equation, which gives Kf as 2.22. We know the relation for alternating stress. Substituting the values in the relation gives, we know the relation for mean stress. Substituting the values in the relation gives. Using the Goodman criteria, we can find the value of factor of safety, which is obtained as n is equal to 0.44. Also, fatigue strength fraction can be obtained from the chart. Substituting the obtained values of fatigue strength fraction and endurance limit, we can find the values of A and B. Substituting the values of A and B in the equation give the numbers or cycles to failure. Let's go to the second problem. Consider a connecting rod made of alloy steel. It undergoes a fully reversing nominal stress of 92 megapascal close to the connecting rod. Estimate the number of cycles to failure. We have additional data. Material is alloy steel. Ultimate strength is 723 megapascal. Test specimen endurance limit is 210 megapascal. Here we have reversible stress as 92 megapascal. Using the Marin's relation, we calculate the values for the surface modification factor Ka as 0.38. Since it is an axial loading, the load factor Kc is taken as 0.85. All other remaining modifying factors are taken as 1. We know the relation for endurance limit. Substituting the values of modifying factors and the test specimen endurance limit value in the equation, we get endurance limit value as 69 MPa. Using the ultimate strength of 723 megapascal, the fatigue strength fraction can be obtained from the chart. We got F as 0.835. Substituting the obtained values of fatigue strength fraction and endurance limit, we can find the values of A and B. Substituting the values of reverse stress value and A and B in the equation gives the number of cycles to failure. For this problem, the number of cycles to failure is 40032 cycles.
Hello everyone. Earlier we discussed about the basics of fatigue and solved problems based on fatigue fundamental equations. In this session we are going to correlate the results of analytical problems with the finite element analysis in Solidworks simulation. This is the plate with the hole problem we solved earlier using fatigue fundamental equations to find the number of cycles to failure. Now we are going to model the same in Solidworks software and run the fatigue analysis to find out the number of cycles to failure. The plate having a length of 70 mm and a width of 25 mm and a thickness of 10 mm. A hole with a diameter 6 mm is located at the center of the plate. First we have to select a plane. I am selecting the front plane here. Now use the center rectangle tool from the sketch command manager to draw the rectangle. After this we have to provide the dimensions. As I mentioned earlier, the length is 70 millimeters and the width is 25 millimeters. Now select the circle from command manager to draw the circle at the center of rectangle. The diameter of the circle is 6 millimeters. As the next step we are applying the thickness. Go to the features in command manager, select the extrude boss base, and now we will give the thickness of 10 millimeters. Now we have to partition the faces of this model through horizontally and vertically. The reason for this is to provide constraints in the simulation stage that I will explain later. We have to create a plane in order to split the face. So that click reference geometry in features command manager and then select a plane and give the distance from the face. We know that it is 12.5 millimeters from the face. Once the plane is created, using it we are going to split the faces. Next, go to the split line in Features Command Manager, select the plane as split tool and then select the faces. The faces we need to split. After that, select OK. Now the model is partitioned in horizontal direction. Next, we are going to partition the model in vertical directions. So that create a plane offset to this particular face, and again click on Reference Geometry in Features Command Manager, and we are giving an offset from the selected face, and the offset distance is 35 millimeters. Now using that plane we are going to split the faces vertically. So that again select the split line from Features Command Manager and select the faces we need to split. After selecting the face, click OK. Now the partition is completed in both directions, that is vertically and horizontally we partition the model. Now the modeling of the part is over, and as the next step we are going to simulation. Here we are going to simulate the plate with a hole problem using Solidworks simulation to find out the number of cycles to failure and compare the finite element analysis with the analytical calculation results. First of all, we have to go to Solidworks add-in Command Manager and select Solidworks simulation. And then go to the new study and click on it. In order to carry out fatigue analysis on the model, a static study has to be carried out first. In the static study, we have to apply the given loading and boundary conditions and to induce the stress values. Then we use these stress values from static analysis to obtain the cycles to failure in fatigue analysis. First, we need to generate a static study. First, select static and then rename it to our convenience. The new name is plate with hole static. Step 1, we need to assign the material to the model. We are going to give the material AISI 1035 steel. In step 2, we are going to constrain the model both horizontally and vertically, and for this reason we provide the partition earlier. First, we are going to constrain horizontally. Right click on Fixtures and select Fixed Geometry. Select Reference Geometry in Advanced Features and select the edges need to be constrained. After selecting the edges, select a Reference Geometry. Then, in order to constrain horizontally, arrest Y and Z directions. After this, select OK. Next, we are going to constrain vertically. Right click on Fixtures and select Fixed Geometry. Go to Advanced Features and select Reference Geometry. Select the edges that we need to be constrained. Select a reference geometry also. In order to constrain vertically, we have to arrest Z and X directions. After this, select OK. As the next step, we are going to apply load. A load of 28 kN is applied on both ends of the plate. Right click on External Loads and select Force. Then select the faces where force is going to be applied. Then select the direction of the force and then enter the force value. After this, select OK. This needs to be repeated on the other side also. As the next step, we are going to mesh the part. Right click on mesh and select create mesh. Enter the mesh parameters value. We are giving the element size 1. Also, mesh is carried out using higher order mesh. For that, go to advanced mesh and maintain Jacobian points 29. Then select OK. Now the meshing is finished. As the final step, we are going to run the analysis. Go to the simulation command manager and run the study. Now the simulation is started. Now the simulation is completed. And we can see the shape of the circle is changed to ellipse. Now we can plot the deflection values. The deflection value is maximum 0.02 millimeters. Now we have to find out the stress values. In order to find out the exact stress values, we have to probe the high stress regions and take the average stress value. Now I changed the deformation. Now right click on legend and select probe. The high stress region is highlighted in red color and we have to click on nodes to find out the stress value. Once the probing is completed, then we can rearrange the stress value. And now we will get the stress value of 322 megapascal. Now the static analysis is completed and we find the stress value. Moving on to the fatigue analysis. First of all, click on new study and select fatigue. And select constant amplitude event with defined cycles. For our convenience, rename the study to plate with hole fatigue. The first step is right click on loading constant amplitude and select add events. Here we can enter the expected loading cycles. We can give us 1 million cycles and then select the type of loading as fully reversed. By default, the previous static analysis we already done is loaded in fatigue simulation. If one or more static analysis is completed, then we have to select manually which simulations we need to be input. In the next step, we are going to apply the fatigue data. Right click and select apply fatigue data. Here we can input the SN curve data based on the material. Here derive the SN curve based on elastic modulus of the material and then based on ASME austenitic steel curve and click apply. Once material data input is completed, we have to go to the study, right click on it and select the properties. There we have to enter two values. First one is main stress correction factor, that is based on Goodman curve, and then we have to give the fatigue strength reduction factor as 0.7. The details of this and how this value is reached is previously explained. Then select OK. Once all the inputs are given, click on Run this study to start the analysis. Now the analysis is started. And now it is finished and the results plots are obtained. And the second plot is the minimum number of cycles to failure plot. In order to get better visualization, we have to change the color code. The region shown in red represents minimum number of cycles to failure. Similarly, in stress analysis, we have to probe for the number of cycles in order to take the exact number of cycles to failure value, because the average values from the nodes give the exact number of cycles to failure value. Since the geometry is symmetric, we have to probe only one region, that is below the whole region. After probing and taking the average values from nodes, we will get the minimum number of cycles to failure. And the value is 11843 cycles. Now the fatigue analysis is finished and the number of cycles to failure for plate with a hole is found out using Solidworks simulation. This is the connecting rod problem we solved earlier using fatigue fundamental equations. Using the equations, we found out the minimum number of cycles to failure. Now we are going to run the fatigue finite element analysis to find out the number of cycles to failure in connecting rod using Solidworks simulation. The modeling of the connecting rod is already completed and we are not presenting it in this webinar. The modeling is based on the approximation of Chevrolet 4-stroke diesel engine connecting rod model available in net. The connecting rod has an overall length of 172 millimeters and the piston pin end have a diameter of 20 mm and the crank pin having a diameter of 53 mm. The piston pin to crank pin end having a center to center distance of 135 millimeters. Similar to the first problem, we have to run a static analysis first. Now click on New Study and select Static. We have to rename it to Connecting Rod Static for our convenience. In step 1, we have to apply material. Right click on Parts and apply material to all. Select alloy steel from material library and click on Apply. In the second step, we have to establish contacts between parts of the connecting rods. Right click on Connections and select Contact Set. In order to find the contact automatically, we have to select the entire assembly. Now the software automatically finds out all the available contacts. We have two contacts available here, that is between the connecting rod and the cap. Select No Penetration option for both the contacts and click OK. Now we have to provide bolts to the respective regions, that is between the cover and the connecting rod. Right click on Connections and select bolts. Select standard counter bore with a nut and select bolt head hole first and then select bolt nut hole. Repeat the same process on the other side also. Now move on to the third step. We have to provide fixtures. The crank pin end of the connecting rod is fixed here. Right click on Fixtures and select Fixture Geometry. Then select the faces to be fixed. Click OK. In the fourth step, we are going to apply load. During the power stroke, a pressure of 18 megapascal is generated in diesel engine. This particular value is taken from internet. The pressure is applied axially through the piston pin end. Right click on external loads and select pressure. The value of 18 megapascal is applied through selected direction using reference geometry. Once the value is entered, select OK. As the next step, we are going to mesh. Right click on mesh and select create mesh. Enter the mesh parameters value. We are giving the element size 1. Also, mesh is carried out using higher order mesh. For that, go to advanced mesh and maintain Jacobian points 29. Select OK. Now the meshing is started. And now the meshing is completed. Once the meshing is completed, we are going to run the analysis. Go to the simulation command manager and run the study. And now the simulation is started. Now the simulation is completed and we can see the stress and deflection plot. We can observe the displacement is maximum value 0.025 millimeters. Now we have to find the stress. In order to find the exact stress value, we have to probe the high stress region and take the average stress value. The high stress region is close to the piston pin end and it is shown in red color. Now right click on legend and select probe. We have to zoom in and start probing. During probing, we have to highlight stress value only. Once probing is completed and rearrange the stress value, we will get the stress value of 92 megapascal. Now the static analysis is completed and we find the stress value. Moving on to run the fatigue analysis. First of all, click on new study and select fatigue. For our convenience, rename the study to connecting rod fatigue. First step is right click on loading constant amplitude and select add events. Then we enter the expected loading cycles. We can give us 1 million cycles. Select the type of loading as fully reversed. Then we already completed the static analysis where we get the stress values. The previous static analysis we completed earlier is already loaded in this fatigue simulation. Next, we are going to apply the fatigue material data. Here we are going to input the SN curve based on the elastic modulus of the material and also based on ASME austenitic steel curve. Once material data input is completed, we have to go to study and right click select properties. There we have to enter two values. First one is mean stress correction factor, that is based on Goodman curve, and then we have to give the fatigue strength reduction factor as 0.33. The details of this and how this value is reached is previously explained. Then select OK. Once all the input data are given, click on Run this study to start the analysis. Now the fatigue analysis is started. And now the simulation is completed and we get the fatigue result plots. Now we get the number of cycles to failure plots. Now we have to change the color coding to get better visualization. The regions shown in red represents minimum number of cycles to failure. Similarly, in stress analysis, we have to probe to find out the number of cycles to failure. Right click on legend and then start probing. After this, starts probing on nodes to get the exact number of cycles to failure. We have to probe on nodes and take the average values from node to get the number of cycles to failure. After probing and rearranging the values, we will get the exact number of cycles to failure as 390255. Now the fatigue analysis is finished for connecting rod and we get the number of cycles to failure for connecting rod. The fatigue analysis for plate with hole and connecting rod using Solidworks simulation software is completed. Now we are going to compare the finite element analysis results with analytical calculation results. In plate with hole problem, the number of cycles to failure value obtained from analytical calculation is 11713, whereas the results obtained from finite element analysis is 11843 cycles. The percentage deviation is 1.1%. In connecting rod problem, the number of cycles to failure value obtained from analytical calculation is 40032, whereas the value obtained from finite element analysis is 390255. The percentage deviation is 2.4%. So we can conclude that there is good correlation between finite element analysis results and analytical calculation results.